All right, so now that we know how to add, subtract, multiply, and divide polynomials, we want to look at other ways of working with polynomials, specifically today, dividing polynomials by factoring. Now, just like long division on polynomials, you've already done this with the integers, and let me give you an example. 6 divided by 3 equals 2. 6 divided by 3 equals 2. We already know that because 3 divides 6. Any number that divides another number is called a factor. Since 3 divides 6, 3 is a factor of 6. We could have done it in the opposite direction. I could have said 6 divided by 2 equals 3, in which case we would have identified exactly the same way that 2 is also a factor of 6. So one way of dividing by factoring is to divide the number 6 divided by 3 equals, we already know that it equals 2, but if I were to factor the numerator into 2 times 3, so that's factoring the numerator, and then factor the denominator, 3, I could just factor partially or factor as a product of primes, usually best to factor as a product of primes, but what I see is that 3 over 3 actually just equals 1, and so I'm left with 2. So even though we don't explicitly do this when we work on the integers, we are, at least in our understanding, reducing a number when we factor a number. Kind of cool, huh? We can do the same thing with polynomials, so let's look at that. So the first thing we want to do is to be able to recognize the factors of terms. Now remember, one term is actually just one monomial. But we want to learn to recognize the factors of monomials so we can write them as a product of factors, just like I did here. I recognized that 3 was a factor of 6 and 2 is a factor of 6. So when I wrote the fraction again, I was able to write 6 as a product of all of its factors, in this case, all of its prime factors. So if we do the same thing with a monomial, we're looking at something like factor 6x squared. So we want to factor 6x squared into all of its factors. Well, we already know that the factors of 6 are 1, but 1 is trivial, and we don't tend to write it because if we wrote it once, we'd have to write it a million times, and that's crazy. We just want the factors that matter when we're operating the number. So we already know that the factors of 6 are 2 and 3, and we know they're factors, and we can check. Are they really factors of 6? Well, let's see. If they are, then when we multiply them back together, we should get 6. 2 times 3 equals 6. They are the factors of 6. And then we need to write the factors, all the prime factors of x squared. Well, that's just x times x. So this is the prime factorization of the term or the number or the monomial 6x squared. Now let's do another one. What about negative 24y squared? Well, 24, if I wrote it as a product of primes, and sometimes it's harder to see a product of primes, so let's go ahead and just do a factor tree where I use prime numbers only. So 24 divides by the prime number 2, leaving 12. 12 divides by the prime number 2, leaving 6. 6 divides by the prime number 2, leaving 3. And so now I can write 24 as a product of primes. So that would be 2 times 2 times 2 times 3 times negative 1. Negative 1 because it's a negative 24. So I would have to take all these primes, multiply them together to get 24, and then multiply it by negative 1 to get the opposite. And then y squared would be y times y. So these are two numbers that have been written in their prime factorization. I've written them out as all of the primes that it takes to multiply to get these two numbers, or each one individually. So when a number is written this way, it's the prime factorization. ran out of room. The prime factorization, meaning it's the prime numbers, all prime numbers that have to be multiplied to give me the original number back. All of the prime numbers that divide the term arranged in a line. Also called product of primes. I like this version better because you know me, I like shortcuts. Product of primes can be written as the pop. So if I say pop this number, it means write this number as a product of primes. So let's do an example. Let's pop 2x to the fourth yz, sorry, I got a little bit lost on my notes, 2x to the fourth yz. We want to pop this number. That means we want to write it as a product of primes. Well, 2 is already a prime number, so the only product I have to write is 2. And then x to the fourth I have to write as x times x times x times x. Y, that's 4 of them, 1, 2, 3, 4 of them, y and z. So if I multiply all these numbers back together, all of these prime numbers multiplied back together will give me the original number back. Well, let's do the product of primes. So let's pop negative 18x cubed y squared. Okay, well, negative means I have to have a negative 1. 18, written as a product of primes, okay, let's say I'm not really sure. I'm kind of sure, but let's say I'm not. 18 divided by 2, the smallest prime, leaves 9, and 9 is 3 times 3. So as a product of primes, I'd write 2 times 3 times 3. Then x cubed, that's 3 of them, 1, 2, 3, and then y squared, that's 2 of them. Again, I have a whole string of prime numbers. If I multiply them all back together, it'll give me back my original number. So we're going to use this to find something called the greatest common factor. So we want the GCF, greatest common factor. That's the biggest factor that both of these numbers contain. If I'm looking for the greatest common factor of 2x to the fourth yz and negative 18x cubed y squared, I would call that the greatest common factor, and I would find it by looking for all the factors that are common to both of these terms. So let's look. Well, there's a negative 1 here, but there's not a negative 1 there. Those aren't common. But look, I have a 2 and a 2. So there's a factor of 2 that's common to both of them. I have a 3, nope, I have an x that's common to both of them. I have another x that's common to both of them. Another x that's common to both of them. I have another x here, but I don't have another x here. I have a bunch of 3's here, but I don't have any 3's here. So I have a y that's common. And z and a y, that's it. So I look for all the factors that are common to both numbers. I string them all up together, and now when I multiply these, 2x cubed y. This is the greatest common factor of these two numbers. What's left after I take out? Well, after I take out 2x cubed y from the first number, all I'm left with is an x and a z. And when I take 2x cubed y out of the second number, I'm left with a negative 1. 3 times 3 is a 9, and a y. Okay, so just hold on to that thought for a little while. I wrote that down because we're going to use that next. But first, the thing is, when you're looking for the greatest common factor, you're looking for all the parts of each number that's the same in both numbers. So now we want to start to use this information. First off, just finding the greatest common factor. Done. We did it. But now we want to use it to divide using the method ME, which is monomial extraction. Notice that this is a monomial. And if I can pull this monomial out, then I can extract it. So monomial extraction, which is a kind of division for polynomials. Let's do that example. So in this case, suppose I have a binomial, 2x to the fourth y z minus 18x cubed y squared, and I'm told to factor this monomial. So my instructions are to factor this binomial. I'm sorry, I just called it a monomial. It's a binomial because it's one number with two parts. That means I want to pull out the greatest common. I'm looking for what divides. Remember, factors divide a number. I want to know what number will divide this whole thing, which means it has to be the monomial that's common to both of them. Well, we've already figured out the greatest common factor using this method. It's it's the monomial 2x cubed y. So I'm going to write division for each of these, 2x cubed y and 2x cubed y. All I'm doing is showing that both terms of this binomial, both terms of this number, divide by 2x cubed y. And then I want to pull it out. I'm going to factor it out. This line stands for monomial extraction, and it means factor out that monomial. So I'm going to write the monomial down, 2x cubed y. And then once I divide both terms by that factor, what's left? Well, 2x to the fourth yz. 2 divides 2, leaving 1. X to the fourth divided by x cubed just leaves 1x. Y divides y, leaving 1. And z. Minus 18 divides 2 by 2, leaving 9. X cubed divided by x cubed is just 1, and y squared divided by y equals y. I guess I can move this parenthesis over. Thought I'd need more room. But if I factor this whole number by factoring each part separately, I end up with 2x cubed y, my greatest common factor, times what's left? xz and negative 9y. Now, this is a process to help you understand what we're doing, but really, when we factor by monomial extraction, most of the time we're just going to do it in our head because most of the problems we'll encounter are pretty easy to find the greatest common factor in our heads. Let me show you how. Or at least let me show you how I do it. So here's a new example. Let's find the GCF, or let's factor, hang on, 18x minus 12. So we're looking to divide this number by the biggest number that divides it, the greatest common factor. So first, let's decide what divides both of them. Well, 18 and 12 have a common factor. The biggest common factor is 6. 18 divides by 6 and 12 divides by 6. That's the biggest number that I can divide both of these terms by. And then x, I could divide this one by x, but this one doesn't have an x in it, so I can't divide by x. So it turns out my greatest common factor is 6 is my GCF. So now I'm going to extract it. I'm going to do ME, right? I'm extracting the monomial 6 from the binomial. And what I get is 6 times, do the division. 18 divided by 6 equals 3. There's still an x. Minus 12 divided by 6 equals 2. And so what I have is 6 times 3x minus 2. Just like when I worked with an integer, saying that 6 equals 2 times 3 divided by 3, I'm doing the same thing here. I'm saying that 18x minus 12 equals 6 times 3x minus 2. Let's check it, and here's how I'd like you to check work. You're going to use a loop that starts from your final answer up to your original problem. And then we're just going to do multiplication, because just like with an integer, how do I know that 2 times 3 is indeed the factorization of 6? Well, if I multiply those two factors together, 3 times 2, did I get 6? If I got 6, then I know that I factored properly. And so we want to check on a polynomial in particular to see if we factored properly. So let's do 6 times 3x. Well, we know that 6 times 3x is 18x. That one's pretty easy in our heads. And 6 times negative 2 is minus 12. Did I get the original problem back? I did. So I have factored and checked my work. Let's do another one. Let's look at negative 5y squared minus 10y. All right. First thing is find the GCF. We're looking for, I'm going to do that in color code, what number divides both of these terms? So we'll start with the sign. This one's negative, so I have a negative 1 and a negative 1 divides both of them. 5 and 10, the common factor 5 divides 5, that's the biggest number that does divide 5, but 5 also divides 10, that's the biggest number that divides 10, other than 10 itself. Now let's look at the variable. I have 2 y's in the first term and 1 y in the second term, so the most I can take out of both terms is one of the y's. So this is my GCF, my greatest common factor, and now we want to go ahead and pull out the monomial. We want to factor it, right? So we're going to pull the 5y out, or the negative, 5y out. When I pull out the negative 5y, all that's left is whatever I get when I reduce each term. So a negative and a negative becomes a positive. 5 divides 5, leaving 1. 2 y's in the numerator, 1 y in the denominator. Well, exponential rules tell us y equals 2 minus 1, so I just get 1 y, and it's positive. Same thing here, 2 negatives makes a positive. 10 divided by 5 is 2, y divided by y is 1, and so I'm finished. So these are the factors of this number. Let's check it. This is the way I want you to check it on your work. I want to be able to read your work and know what you've done, and this is what I call correct algebra. So I'm going to distribute again. So I'm going to, if I divided or if I factored to get here, then I'm going to multiply to get here. So negative 5, negative and a positive is a negative. 5 times 1 is 5. Y times y is y squared. Negative and a positive is a negative. 5 times 2 is 10. I have 1 y and 0 more y's. That gives me 1 y. I ended up right back where I started, so I know that my factoring is correct. All right, let's go out with a bang and do a hard one so we can prove we know what we're doing. 12a to the 4th b minus 20a cubed b squared plus 8a squared b cubed. Okay, I have 3 terms, so I'm looking for the greatest common factor for each term. I can start with the sign. This one's positive, negative, positive, so the sign isn't going to make any difference. Then I can look at 12, 2, and 8. What's the biggest factor that all 3 of them have? Well, 2. It's a pretty small number, but I can't divide 2 by 8 and get an integer. I can't divide, so 2 is my biggest number. Now let's move on to the a's. What's the biggest number of a's contained in each of the terms? Well, a squared. So that's my biggest number of a's. And my biggest number of b's is 1. I have 1b here, at least 1b here, and at least 1b here. So this is my greatest common factor, found without having to write a pop, but understanding that writing as a product of primes, like I did at the beginning, is how we got there. Now I'm going to extract. I'm going to pull that factor out of the original number. I pull this factor out of each term by dividing each term by that number. So I'm going to pull that 2a squared b out and see what I have left over. Well, 12 divided by 2 is 6. A to the fourth minus 2, so a to the 4 take away 2, just exponential properties. B divided by b is 1, so I'm done with that one. Minus 2 divided by 2 is 1, don't have to write it down, just is. A cubed minus 2 means I have an a left behind. B squared minus b means I have 1b left behind. Plus 8 divided by 2 is 4. A squared divided by a squared is just 1. And b cubed minus the 1 in the denominator is b squared. All right, now let's check my work again. So I'm going to multiply the first monomial to the first term in the second number. 2 times 6 is 12. A squared is a to the fourth. B times no more b's is b. Minus, positive and a negative is a minus. 2 times 1 is 2. A squared plus another a, so there are 2 a's plus 1 more is 3 a's. And then b and another b is 2 b's. Plus, because a positive and a positive, then 2 times 4 is 8. A squared, and no more a's. 1b and 2 more b's is b cubed. Did I get back the original problem? I did. I got back exactly what I started with, and so I know that I've done my work correctly.